On Friday, we started talking about the factors that determine relative acid strength. We talked about the element effect. We mentioned that the element effect is not always the most important of the four effects. The book is an error in this case. This is an excellent book. It's the best book for learning organic chemistry, in my opinion, but it is not perfect. And this is one key area where it is not accurate. So element effects are not always the most important of the four effects, as we will discuss in more detail today. We'll continue on with inductive effects and the other two. Then we'll talk about some of the common acids and bases that we're going to see throughout the year in organic chemistry. And then we'll conclude with a discussion of the acid-base chemistry of aspirin, a very common pharmaceutical agent. Okay. We won't quite finish chapter 2 today. We'll leave Lewis acids and bases for Wednesday before we jump into chapter 3. So the inductive effect is the second of our four effects that we're going to discuss. And the inductive effect is an effect on relative acid strength caused by electronegative atoms that are not connected to our acidic hydrogen, meaning that they are somewhere else in the molecule. So as an example of the inductive effect, we have here two compounds, ethanol on the left here with a pKa of 16, trifluoroethanol on the right with a pKa of 12.4. So based on our discussion of pKa, you recognize and identify trifluoroethanol as the stronger of these two acids. How much stronger is it? Okay, close to 10,000, right? No, that's correct. So what's the difference in pKa units here? Right, 3.6, right? So it's between 3 and 4. If the difference was 3, what would the difference in relative acid strength be? Okay, 3 orders of magnitude or 1,000, right? If the difference was 4, what would it be? It would be 10,000. So that tells you that the difference in relative acid strength is somewhere between 1,000 and 10,000. If we measure it, it turns out to be about 4,000. Okay, so trifluoroethanol is about 4,000 times stronger as an acid than ethanol is. Why? And please don't just say the inductive effect, because I've given that to you. We have to go much deeper than that in understanding why trifluoroethanol is a stronger acid than ethanol. Okay? Who would like to take a stab at explaining this for us? Yes, please. Okay, so you're saying the electronegative fluorine can pull on the electron density and stabilize. And when we're talking about pulling on the electron density and stabilizing the structure, are we talking about the acid or are we talking about the conjugate base? Exactly. It's very important when we are considering these factors and their impact on relative acid strength that we be referring to the conjugate base. As we mentioned on Friday, any structural feature that lowers the energy of the conjugate base makes it more likely to be formed in an equilibrium. Equilibria will go in the direction of the more stable product. So if we lower the energy of our conjugate base, make it more stable, it will form more readily, meaning the acid will dissociate or be deprotonated. So what you're saying is that the electronegative fluorines can pull on electrons from the negatively charged oxygen in the conjugate base, therefore stabilizing it. So let's take a look at that. Let's draw that on the board. So first we'll draw the conjugate base of ethanol, okay, which is known as ethoxide. Okay, and then over here we will draw trifluoroethoxide, the conjugate base of trifluoroethanol. Okay. All right, so we know that fluorine is highly electronegative. So our 3 carbon fluorine bonds are all going to be polarized towards the fluorines. So that gives this carbon a fairly substantial partial positive charge. It's involved in 3 polar bonds that are all polarized away from it. So we're going to have a pretty good partial positive charge here. That partial positive charge is going to cause this carbon to attract the electrons in the carbon-carbon bond more strongly than that carbon is. Okay? So it's not really a dipole. We don't really have a great way of showing it. So I'm just going to draw this, but just recognize that's not really a dipole. That's just my way of showing that this carbon with its fairly substantial partial positive charge is pulling on the electrons in this sigma bond, which again allows it to pull on the electrons in this carbon-oxygen sigma bond and delocalize, not through resonance, but delocalize through induction, the negative charge on this oxygen atom. Okay? And with no electronegative atoms in this molecule, in ethoxide, other than the oxygen that already bears the negative charge, there's no inductive effect and no ability of that conjugate base to stabilize or delocalize that negative charge. Okay? So we have electrostatic potential maps here of these 2 conjugate bases. And we see yellow color in trifluoroethoxide as opposed to the red color. There's a hint of red here. But that yellowish color means that this oxygen atom is less electron rich than the oxygen in ethoxide. And that is due to induction delocalizing that negative charge. And that's due to the electronegative fluorines pulling on the electrons through the sigma bonds, connecting it to the oxygen. Okay? So inductive effects are manifested through sigma bonds. Any questions about the inductive effect? Okay, yes? Yes. So you will have an inductive effect if there are electronegative atoms elsewhere in the molecule. How much of an inductive effect you will have is a question of debate, which we'll discuss in a moment, but you will have one. Yes. Okay. Right. Yeah, so that question leads into our next topic here. So a few points related to the inductive effect. The more electronegative the atom is, the stronger the inductive effect will be. So let's say we have trichloroethanol. Is that going to be a stronger or a weaker acid than trifluoroethanol? Weaker acid. Why? Yes, and why is its conjugate base less stable? That's right. So this is a less electronegative atom. So those chlorines are not going to be able to pull on those electrons as strongly as the fluorine will. Okay? You might say, but wait a minute. Chlorine is below fluorine in the periodic table. It's larger. Which effect is that, where size matters? That's the element effect. The element effect only applies when it is the atom that is attached to the acidic hydrogen. Okay? So some of you probably thought, you don't have to identify yourselves, but I'll bet there are at least a few people in the audience who thought that trichloroethanol would be a stronger acid because chlorine is bigger than fluorine. That's not correct because you only consider the size of the atom if it is the atom attached to the acidic hydrogen. In this case, it is not attached to the acidic hydrogen. It is elsewhere in the molecule. So all you consider is the electronegativity. Any questions about that example? Okay, so in regards to inductive effects, one thing to note, the more electronegative the atom is, the stronger the effect. Another thing to note with the inductive effect is that it is additive. The more numbers of the higher quantity of electronegative atoms that you have in your molecule, the stronger your inductive effect will be. So what if we had difluoroethanol? Would that be a stronger or a weaker acid than trifluoroethanol? That would be a weaker acid, exactly. Less of an inductive effect stabilizing its conjugate base, making it a weaker acid. Okay? And then, in response to one of your questions that was asked, the inductive effect also depends on the distance between those electronegative atoms and the negatively charged atom in the conjugate base. The further away the electronegative atoms are, the weaker the inductive effect will be. So if we put in another carbon in the chain, we would call this trifluoropropanol. Would it be a stronger or weaker acid than trifluoroethanol? It would be a weaker acid because we have more sigma bonds. We have one more sigma bond in between the fluorines and the oxygen than we do here. So we're going to have a weaker inductive effect. So the inductive effect is weaker if those electronegative heteroatoms are further away from the negatively charged atom in the conjugate base. Okay? So it depends on distance, it depends on the number of electronegative atoms you have, and it depends on the atoms themselves. The more electronegative the atom is, the stronger the effect will be. Okay? Another thing to note about the inductive effect is that it is the weakest of the three effects. Right? The book tried to tell you that the element effect was the strongest. I'm telling you it's not, and I'll show you why it's not in a moment. But the one generalization I am comfortable making is stating that the inductive effect is always the weakest, meaning the impact of the inductive effect on relative acid strength is going to be smaller than the impact of either the element effect or the resonance effect or the hybridization effect. Okay? So the difference is, this is one of the strongest ones you'll see because this is 3 of our most electronegative atoms very, very close to the negative charge in the conjugate base. So you're not going to find an inductive effect stronger than the one here. Most of them are going to be on the order of 1 to 2 pKa units. Okay? Whereas with the other 3 effects, sometimes we'll see them be a difference of 10 pKa units or more. Okay? Any questions about the inductive effect? Okay, let's talk about the resonance effect now. And in the resonance effect, what we're going to see is resonance stabilization of the conjugate base. Remember, all these effects deal with the conjugate bases because those are the products of our acid-base reaction, whereas the acid itself is a reactant. So let's compare, we'll use ethanol again. So ethanol, we already know its pKa is 16. Let's compare it to acetic acid. As its name suggests, it is acidic. It's significantly more acidic than ethanol, pKa of 4.8. Who would like to raise their hand and explain why acetic acid is significantly more acidic than ethanol? Okay, Minnie? So in the conjugate base of acetic acid, you're saying that the double bond can be in more than one place, meaning that there are 2 resonance structures you can draw for that conjugate base, right? Yes, exactly. So the conjugate base of acetic acid is stabilized by resonance. So we'll draw that out. And we always use our curved arrows when we're showing, let me draw these lone pairs in too. When we're showing resonance stabilization, we draw out the lone pairs and we use the curved arrows. Okay. So here's our resonance stabilization of acetate, or the conjugate base of acetic acid. What do we notice about these two resonance structures when we compare them to each other? Yes. Okay, they're equivalent to each other. And what do we know about the degree of stabilization due to resonance when the resonance structures are equivalent? This was from chapter 1. You get the highest amount of stabilization from resonance when you have equivalent structures, meaning that our hybrid is going to be halfway in between. So we can draw the hybrid structure. It'll look like this. It'll have minus 1/2 charges on each of those oxygens. And so we have a significant resonance stabilization of that anion. Question? When I say that I didn't say they were equal, I said they were equivalent, so that's not quite the same, meaning that they're going to be equivalent in energy. There's no difference in energy between these two structures. Yeah, if you just rotate one, you get the other. So yes, they indicate, when you have that, that indicates that the charge is going to be shared equally by the atoms that have them in the individual resonance structures. Okay, question? Yeah, exactly. So the electron density, because of this resonance stabilization, the negative charge is shared equally by those oxygens. It's spread out over a much larger area than the negative charge in ethoxide, which we have right here. We cannot draw a resonance structure of ethoxide, so the negative charge here is just anchored on that oxygen. Now that oxygen is electronegative, but we don't have the ability to delocalize that negative charge. So this conjugate base here, ethoxide, will be significantly higher in energy than the conjugate base acetate. And we see that here. On this particular figure, they didn't decrease the redness here, but what they did was they showed that the red area was much larger than the red area here. And so that's how we can see the delocalization of the negative charge in acetate that we don't have in ethoxide. Okay, question? Yes. You have to be very careful when comparing electrostatic potential maps because they could have been generated with different scales. And so the book, when you're comparing electrostatic potential maps that are in the same figure, you can make a good comparison, but you can't compare them from one figure to another. Otherwise, it's kind of like apples and oranges. Okay? So you can compare these two to each other, and you can come to a conclusion from that. And you can compare these two to each other, but you don't want to try to compare an electrostatic potential map from one figure to another, because the scale that was used to generate those different colors is going to be different. Yes, yes, that's very safe to say. Yes, and because of the large difference in the magnitude, the difference in pKa units that we have here, more than 10 to the 11th, we have a much, much bigger difference in relative acid strength due to the resonance effect than we do due to the inductive effect. Okay, and that is going to be general, namely that the inductive effect is going to be more modest than the resonance effect in terms of its impact on relative acid strength. Okay? Questions about resonance effects? So I mentioned to you that the element effect is not always the most important one. So here's an example of that. Okay, this compound is called methane thiol. If we were only using the element effect and comparing methane thiol to acetic acid, which one would we conclude is a stronger acid? If we compare oxygen to sulfur, which one would we say is going to be a stronger acid? We'd say sulfur because it's larger, right? They're in the same, we go to our periodic table. Sulfur is below oxygen, it's a larger atom. Having a negative charge on the larger atom is going to be more stabilizing. So if all we used was the element effect, we'd say this is a stronger acid than that. As you might imagine, since I'm bringing it up as an exception, it is not a stronger acid than acetic acid. It's stronger than ethanol, right? We could compare these two because neither one has resonance. But here, where we have acetic acid, where the conjugate base is stabilized by resonance, this is actually more acidic than that. So this is the example I'm showing you to demonstrate that it's not true that the element effect is always most important, okay? But before you get too concerned and worried, I'm not going to ask you questions where you have to pit one effect against another unless it's the inductive effect versus any others, because I've already told you the inductive effect is weaker than the other three, okay? So I'm not going to ask you to weigh the resonance effect against the element effect because you can't really do that generally. Question? If you were comparing these two and using the element effect, which one would you say is stronger? Right. So you have effects kind of going against each other, right? The element effect would say this is more acidic. The resonance effect would say this is more acidic. And this example shows us that in this particular case, the resonance effect is stronger. They could. If we had a sulfur that was resonance stabilized, then yeah, we'd get increased acidity there, but we didn't in this particular case. Okay? This example is just to show you that you can't count on what it said in the book about the element effect always being most important. Okay? All right, any other questions about the resonance effect? Okay, yes? Well, it depends not necessarily on the identity of the atom, but on the resonance structures themselves. If they're equivalent to each other like they are here, we're going to have a really strong resonance effect. If you have a major contributor and a minor contributor, the resonance effect would not be as strong. So it's not necessarily the identity of the atom, but the structures of the resonance structures. Are they equivalent or are they not? That's going to dictate whether we have a really, really strong resonance effect or a not as strong resonance effect. Okay? All right, so let's look at the hybridization effect. So the hybridization effect is going to deal with different hybridizations of the atom attached to the acidic hydrogen. And it's going to refer to hydrogens attached to carbon, which are generally not very acidic because carbon is not very electronegative. So these are all going to be weak acids that I'm going to show you. So this is ethane here. This is C2H6. These are two CH3 groups. And then here I've drawn for you ethylene with a double bond, C2H4. And then over here I'm going to actually draw out the hydrogens because it would look really funny if I didn't, in my opinion. This is acetylene, C2H2. Okay? These are all weak acids, but there are significant differences in their relative acidities. pKa of ethane depends on which source you look at, anywhere from 50 to 62. The source I'm using will say pKa of 50 for ethane. pKa of ethylene, 44. Still a very weak acid, but a measurable difference, 10 to the 6th, right? 1,000,000 times, pretty big difference. Acetylene, an even bigger difference, pKa of 25. Still a weak acid, but 10 to the 19th stronger than ethylene. Who would like to raise their hand and explain the differences in relative acidity here? Okay, please, in the back. Yep. Okay, so I really like the way you started out and went straight to the conjugate bases, because when we are uh, weighing the relative acid strengths, trying to determine relative acidities, we always need to go to the conjugate bases. So let's start there with that part of your explanation, and we'll draw out the conjugate bases of each of these species. Okay? All right. So next part of your answer, let's look at the lone pair and what kind of orbital that lone pair is located in. What kind of orbital is this lone pair located in? Okay, that's an sp3 orbital, right? What kind of orbital is this lone pair located in? sp2, and here, sp, okay? Based on these pKa numbers, we can identify which of these is more stable and lower in energy. Which is the most stable? The one here on the right, right? Okay, so we know that having that lone pair in an sp orbital is going to be the most stable situation of all of these three. But why? Who can explain why that is the case? Okay, Claire? Okay, excellent. So we look at percent S character. We know it's 25 here, 33, 50. So which of our atomic orbitals is closer to the nucleus, S or P? S. So if we have higher percent S character of a hybrid orbital, then that hybrid orbital will be closer to the nucleus. And therefore, electrons in that hybrid orbital will be closer to the nucleus. Okay? So in the conjugate base of acetylene, this lone pair is held closer to the nucleus than the lone pair in the conjugate base of ethylene, which in turn is held closer to the nucleus than the lone pair in the conjugate base of ethane. Okay? And of course, being closer to the nucleus, that negative charge is stabilized more by that stronger attractive force. Okay? So here, we're not delocalizing electrons like we were in the other two effects we talked about today. What we're doing is stabilizing a negative charge by having it be attracted more strongly to the nucleus. And we have electrostatic potential maps that show that comparison as well. And in this case, what they do is just decrease the red color as you go from left to right. And this bullet point summarizes exactly what we talked about. As the lone pair of electrons is held closer to the nucleus, we have less red on that carbon, indicating a more stable anion due to that stronger attraction to the nucleus. Okay? Any questions about the hybridization effect? Then I'll ask you a question. Which of these three compounds has the strongest carbon-hydrogen bond? Okay, you say the first one, the one on the right or left. Why? Okay, so you're saying that this, because it is less acidic, must have a stronger carbon-hydrogen bond, right? But that doesn't fit with what we learned last week when we said that the shorter bonds were stronger, and we said that the bonds to the sp with the sp hybrid orbitals would be shorter. So higher percent S character means shorter bonds and stronger bonds, okay? So I'm glad you were confused by this question because this seems like it's inconsistent. We would say that this has the stronger carbon-hydrogen bonds, and it does. But we've just said that this is the stronger acid, and it is. So how do we resolve those two things? Well, we resolve them by explaining that when we measure bond strength, we are measuring the amount of energy it takes to break a bond spontaneously in a homolytic fashion, to cleave it and have the two electrons go to the different atoms Okay? And that is a different way of cleaving a bond than what we do in an acid-base reaction. Okay? So yes, this bond is stronger, meaning that it would take more energy to just break that bond in a thermal fashion. But in an acid-base reaction, which is different, we're able to remove this proton more readily than this one. Okay? So the reason I brought up that question was not to trick you or make you feel confused, but just to make the point that there is a difference between bond strength and acid strength. We're measuring two different properties. They are not the same. Okay, so that's how we're able to reconcile that seeming inconsistency. Any questions about that? Okay, so we've gone over all four of the effects: element on Friday, inductive, resonance, and hybridization today. So we should be ready to practice. Let's get our eye clickers out. We have a question here. We have 4 acids on the screen. Please choose the strongest acid. You may go ahead and talk to your neighbors to answer this question. Okay, let's give you about maybe 15 more seconds or so to come up with your final answers here. Any more answers coming in? Okay, there's one. There's another one. All right, going once, going twice. I guess that's it for today. Okay, so as you made this comparison, which of our 4 effects did you use? The inductive effect. Yes, why? Why did you choose the inductive effect? Who can raise their hand and say why you chose the inductive effect? Yes, Claire. Right. Exactly. So you identified that the only difference in these acids was in atoms that were not attached to the acidic hydrogen. Therefore, you had to use the inductive effect. And that's important because if you went for the element effect, you'd get the wrong answer. Okay? So it was important to identify the inductive effect. And identifying the inductive effect as the key effect leads us to conclude that which of these 4 is the strongest acid? A, exactly. Very good. Okay? Are these acids, are the conjugate bases of these acids stabilized by resonance? Yes, but why can't we use the resonance effect to distinguish between them? It's all the same, exactly. So we have to identify the factor that's different between these acids in order to determine which one is the strongest acid. Okay? Any questions about this problem? Okay. So the book has a very nice figure, a nice summary table. One of the great strengths of our textbook is that it has excellent summary figures and tables that very concisely summarize a lot of the key concepts of organic chemistry. And so this one is a great table that very concisely defines the 4 effects that we've talked about. It shows the examples that we've gone over in class. It's important when you use these figures not to just memorize them, okay? We try to minimize the memorization in the class. If all you do is memorize this table, you're not going to understand a relative acidity well enough. What you have to do is understand the underlying reasons why acetic acid is more acidic than ethanol. Don't just memorize that it's more acidic. Understand why. So the proper way to use these tables is to read through them and then ask yourself, do I know why trifluoroethanol is more acidic than ethanol? Do I know why acetic acid is a stronger acid than ethanol? Do I know why acetylene is the strongest of these three acids? And if you can clearly explain it, and better than explaining it to yourself is explaining it to a study partner, if you can very clearly explain it to your study partner, then you know you have a good understanding of relative acid strength. Questions? Yeah, that's the element effect. That's the size if it's the column. If it's in the same row, it's the electronegativity that matters. So if we're comparing across a row here, you'd say HF is the most acidic. HF is more acidic than water, which is more acidic than ammonia, which is more acidic than methane. So the element effect has two components. Going across a row, it's electronegativity. Going down a column, it's the size. Okay, other questions? All right, so let's take a look now at some of the common acids and bases that we will encounter throughout the semester. Acid-base chemistry is a part of many different types of reactions in organic chemistry. And so we're going to see, once we start learning reactions in chapter 7, we're going to see acids and bases constantly from then until the end of the year. Okay? Sometimes we'll need strong acids for reactions, other times we'll need weak acids, sometimes we'll need strong bases, other times we'll need weak bases. So it's important to be able to recognize these species and be able to identify them. So for strong acids, when we need a strong acid for an organic reaction, many times we're going to use the familiar inorganic acids that you would have learned in general chemistry. And as we said on Friday, if it was a strong acid in general chemistry, we consider it a strong acid in organic chemistry. Okay? But these species are soluble in water. In chapter 3, we're going to talk a bit about solubility properties, and there's the like dissolves like rule that you would have learned. And these acids don't dissolve in organic solvents. So sometimes we need a strong acid that will dissolve in an organic solvent as opposed to water. And that's where the strong acid I've shown for you right here comes into play. This compound is quite organic. You see it has 7 carbons in it. It also has 8 hydrogens. So this is going to be soluble in organic solvent. Okay? Its name is para-toluene sulfonic acid, which you have no need to memorize whatsoever. It's a very lengthy name. We like to abbreviate long names in organic chemistry. We call this PTSOH. Okay? So this abbreviation stands for this strong acid. As you can see from the pKa value I've drawn for you, it is quite a strong acid. Okay? You might be wondering, why is it a strong acid? What makes it a strong acid? Well, that would be a good problem for you to work on at home when you're reviewing these notes. Okay? Draw the conjugate base and try to figure out why that is such a strong acid. Specifically, why is it a stronger acid than acetic acid? Okay? When we need weak acids in organic chemistry, acetic acid is probably the most common one that we will see. Okay? Sometimes it's abbreviated HOAC, sometimes it's abbreviated ACOH, sometimes it's drawn out, but this is probably our most common weak acid that we will see in organic chemistry. We've got its pKa up here on the upper board, 4.8. So you ought to be able, it is kind of an advanced problem, kind of on the border of our challenge type problems, but you should be able to look at the conjugate base of acetic acid compared to the conjugate base of para-toluene sulfonic acid and explain why this is a stronger acid than that. So that's a good exercise for you to do at home. Question? So the acidic proton here, we know what it is because we've drawn it before. Which one's the acidic proton here, do we think? The one on the oxygen. All the other protons are on carbon, and we know that those are going to be very weakly acidic. So indeed, it is this hydrogen right here. Okay? All right. So in terms of bases that we will see in the class, this figure here shows us some of the strong bases that we will encounter. And we learned that our prototypical strong base from general chemistry, hydroxide, is still a strong base in organic chemistry. It is the conjugate base of water, or H2O. In organic chemistry, we have alcohols that are kind of similar to water because they have an OH group, but they have a carbon attached to the oxygen instead of two hydrogens. These are simply the conjugate bases of alcohols, right? Methoxide, ethoxide. We've already seen ethoxide because it was part of our comparison for the inductive effect as well as the resonance effect. So these are conjugate bases of alcohols, and they are of very similar basicity to hydroxide itself. So these oxygen bases are very comparable to each other in basicity. All of the bases that are on the screen here are strong bases. But my question for you is, comparing the oxygen bases to the nitrogen bases, which ones are stronger bases? Okay, you're willing to take a stand and say nitrogen. Why? Okay. Okay, excellent. So you said that nitrogen is less electronegative than oxygen. I'm going to rephrase the second part of what you said a little bit. And I'm going to say that because nitrogen is less electronegative than oxygen, it's holding on to its lone pairs less tightly than oxygen is. So those lone pairs are more available to function as a base. Okay? So that makes these bases stronger than these bases. Okay? Now, if you were thinking, oh, oxygen is more electronegative, therefore it's going to be a stronger base, you were thinking more in terms of acids than you were in terms of bases, right? If we were looking at acid strength, we would say water is a stronger base than ammonia because oxygen is more electronegative. But when we're thinking about relative base strength, it goes the other way around, okay? If you have the negative charge on a more electronegative atom, that's going to be more stable. Those electrons are going to be held more tightly. Therefore, these species will be less basic than these species. Question?
Because all these rules we talked about are kind of when we're comparing the relative acidity.
Yes.
Can you flip them to look at the relative basicity?
Okay, so can you flip the rules to talk about relative basicity? There's really two, in my mind, there's two ways that are effective, that make sense when trying to determine relative base strength. Okay. One is to just determine relative acid strength of the conjugate acids. Okay. So what's our conjugate acid of NH2 minus? NH3. Conjugate acid of OH minus? Okay, what's a stronger acid, water or ammonia? Water's a stronger acid, therefore its conjugate base is weaker. So that's one way to do it. That's the long way to do it, but since we're more used to comparing relative acid strength, that's kind of the safe way to do it. Okay? The shortcut way is what we were just talking about in terms of electronegativities, recognizing that a base will be stronger if its lone pairs are more available. And so in this particular case, the lone pairs on the less electronegative atom are more available. The ones on the more electronegative atom are held more tightly and therefore less available. If you had a lone pair that was stabilized by resonance, it would be less available. So if we were looking at acetate, it's going to be less basic than ethoxide because the lone pair is less available due to the resonance stabilization. So that's kind of the shortcut way to look at how available the lone pair is to function as a base. Any questions? Okay. And then hydride, what's the conjugate acid of hydride? If we protonate H minus, what do we get? H2. So this is a very strong acid, or very strong base, I'm sorry, because H2 is a very weak acid. Nobody would really think of H2 as being any kind of an acid. So this is a very strong base. In fact, hydride and both of these bases are strong enough that they can deprotonate acetylene. Okay? Right? pKa of ammonia is like 38. pKa of hydrogen is 35 to 40, somewhere in that range. So these bases are strong enough to deprotonate acetylene, showing us that the hybridization effect can be stronger than the element effect. Okay? All right, any questions about our strong bases? Okay, sometimes we need weak bases in organic chemistry. And the weak bases we use the most are neutral nitrogen compounds. We know that negatively charged nitrogen compounds are going to be strong bases. Neutral nitrogen compounds are going to be basic still because they have a lone pair, but they're going to be weak bases. So this one is called triethylamine. pKa of the conjugate acid is 10.75. Okay? So that is the conjugate acid. You protonate this nitrogen, you get an ammonium ion. You get a weaker acid than water. Or sorry, I'm going to take that back. You get a stronger acid than water. Therefore, this is a weaker base than hydroxide. Okay? So amine bases such as triethylamine are very common weak bases in organic chemistry. And then there's another weak base, weak nitrogen base that we'll see. This one is called pyridine. Both pyridine and triethylamine smell really bad. So if you're using them in the lab, you definitely know it because they stink. pKa of the conjugate acid of pyridine is 5.2. So which of these is a stronger base, triethylamine or pyridine? Triethylamine is a stronger base. Why? Has a weaker conjugate acid. Exactly. Why is the conjugate acid weaker? We won't know until 352. This is a topic that we'll revisit in 352. We don't know all the principles to explain this, but based on the pKa values I gave you, you can recognize this is a stronger weak base, this is a weaker weak base. Okay? Any questions about our acids and bases that we'll see? All right, in the last couple minutes, let's talk about aspirin. Aspirin is this compound down here, acetyl salicylic acid. It has a great history that we don't have time to go into, but salicin is a naturally occurring compound that comes from willow bark that has been used since Greek times to treat pain and fever. It was discovered you could convert salicin into salicylic acid, and it was more effective as a painkiller, but it caused irritation to the stomach lining. And in the 1890s, a chemist working at a company called Bayer in Germany found that you could make acetyl salicylic acid, and it was less irritating to the stomach, and that was the world's first commercial pharmaceutical agent, aspirin. Okay? But what we're more interested in the history is the acid-base chemistry of aspirin. Okay? So we're going to draw that for you here on the board. Okay? So hopefully you recognize the hydrogen on the oxygen is going to be our acidic hydrogen in aspirin. So we're going to have a base that's going to deprotonate that. And then we're going to generate our conjugate base of aspirin and the conjugate acid of whatever base we used. Okay? The pKa of aspirin is 4.5, I believe. Yep, 4.5. Very similar to that of acetic acid, and you ought to be able to figure out why that is the case. But what we're going to talk about aspirin is what it does in our body once we ingest it, okay? After we swallow aspirin, where does it go? It goes into our stomach. What kind of environment do we have in our stomach, acidic or basic? Our stomach is acidic, okay? So in the stomach, would you have a higher concentration of B or BH plus? You'd have a higher concentration of BH plus. So thinking about Le Chatelier's principle, if you had a higher concentration of BH plus, would that favor aspirin or its conjugate base? Aspirin itself, having a higher concentration of BH plus, would cause the conjugate base to get consumed and form more of aspirin, okay? So in the stomach, aspirin itself, as the acid, will dominate in terms of its concentration, okay? Let's say the aspirin passes through the stomach, it would end up in the intestines. The intestines happen to be a basic environment, okay? So in the intestines, you'll have a higher concentration of B than you will of BH plus. So which of the two forms of aspirin will dominate in the intestines? The conjugate base, because of the fact that the intestines are basic. So the conjugate base will dominate. Okay? Now, why this is important is that aspirin has to be absorbed into the bloodstream in order to work. We have to get it into the bloodstream for it to be able to travel to the sites of pain or inflammation that we have in our body. Okay? To be able to be absorbed in the bloodstream, it must cross cell membranes. Cell membranes are nonpolar. Which form of aspirin do you think is more able to cross cell membranes, the acid or the conjugate base? The acid, yes. The conjugate base is ionic. So that ionic conjugate base is not going to be able to cross cell membranes. This has polar functional groups, but it's much less polar than the conjugate bases, so it is able to cross cell membranes. So that means that aspirin is absorbed into the bloodstream in the stomach rather than the intestines. Okay? So that's how aspirin's acid-base chemistry affects its biological activity. Any questions? All right, we'll stop there for today. We'll finish up with Lewis acids and bases and then jump right into chapter 3 on Wednesday.